Thank you very much for the kind introduction and kind invitation to this conference. So, well, my expertise is in fiber diffraction, but I'm not talking about fiber diffraction today, and more classic subject of moisture sensitivity of wood. So this is very classical images if you go learn wood physics or wood science, where you have, this is a wood piece in my home for firewood. And you see those cracks. You don't have to do fatigue test. It just cracks by just drying. And this is an image in the textbook of Roger Rowell. There was a myth in the 19th century Germany that in ancient Egyptian was breaking this granite stone by wood chisel. So they drill some small hole, put some densified wood and pour water, and then can split the rocks. And actually, he took this photo when he was visiting this place. So this is his direct observation by Roger. Now, this is a more problematic situation, I think. I took the photo in University Laval in Canada. Just I happened to visit, and you see very nice construction with glulam. But if you have a closer look, you see also this kind of checking close to this this joint, metal joint. So this is something that is related to the dimensional stability of wood, and probably because if you dry on the surface or if you have condensation to the metal plate, if it's cold, you can have migration of water, you have heterogeneous swelling and shrinking behavior, and that is creating cracks without any external stimuli. You don't have to do fatigue, or you don't have to apply so much force. And then it might, because you dimension so large that you have so much safety that it won't break. But if you want to optimize the usage of timber, this kind of behavior is something that is problematic. And I also think that I talked to Bing yesterday that this usage of metal in combination with wood is problematic because you will have huge gap in property and also temperature, conductivity, some conductivity of the material is a problem. I don't know why it's like this. There's a problem with two overlap, but so behind is what is my expertise of scattering experiments, and we are looking here what's happening inside the wood when we change the moisture content of wood. So the different color plot is the scattering curve perpendicular to the fiber direction. Here it is the crystalline region where you see that the crystal is not changing. And here in the very small angle, what we are looking at here is the contrast between the air and the cell wall surface. So if you fill the lumen with water, now the interface is water and the cell wall, so you have the smaller contrast, so you see that the intensity decreases. And this intermediate region, this is what we are looking at inside the cell wall. And what we see here is up to a certain relative humidity, like 30% relative humidity, you see an increase in intensity because the contrast between the matrix, which is hemicellulose and lignin, is swollen by water, so the density decreases, whereas the crystalline part is not changing. So what we see here is increase in scattering because we see larger contrast, And also we see the shift in the peak towards the low angle, which means that we have the swelling of the structure at this nanoscale. I don't know if I can, oh, okay. I don't know why it was overlapped like, but there's a very interesting paper in 58 by, so very important, oh, sorry. Very important US Department of Agriculture, the swelling pressure of wood. So so we saw that it can split granite. We see that it can break itself by its own swelling power. So what is the pressure of wood when it swells? The experiment is relatively simple. What they do is they have a cylinder where they know the elastic property. They fill in the inside. I'm sorry. Densified wood. So in this, well, he densify it to a different degree and fit into this cylinder after equilibrating at 30% relative humidity, and then put contact to the 100% humidity air, and then just measure the strain of this ring over time. So it's a very long experiment because you see it's in days. So you say that, okay, my sample did not swell in 1 week, but what you see here is the buildup of pressure over days up to 270 days. So they just measure the deformation of the ring over time. And at the end, they get something like 70 megapascal. For this kind of, it depends on the density of the starting wood. The more dense is the starting wood, the higher is the swelling pressure. But it's the order of 100 megapascal, which is huge. In this paper, he also explains the origin of this pressure. And the idea is you can actually consider the free energy of the vapor, and you consider that bringing 1 mole, the pressure you feel is related to the fact that you are going to insert water molecule. So that is the difference between adsorption and swelling, because you are modifying the structure, you are inserting more water molecule into the structure so that the volume of the material changes. And because you know that one mole of water occupies 18 centimeter cube, and this is the free energy of vapor is just related to the relative humidity, and so you can just calculate the pressure from the isothermal sorption isotherm. So for wood, you can go to the wood handbook, which has a compilation of sorption isotherm. In general, you express the water content at equilibrium as function of relative humidity. And in this handbook, you have a compilation for a different temperature. The lower the temperature you have, the more adsorption you have. But now because we wanted to relate it to the free energy, then you invert just the plot. The water content as the relative humidity in equilibrium as function of water content. And this is giving directly the swelling pressure from the previous assumption. So if you are very, very dry, if you start in the experiment by the USDA guy, it was equilibrated first at 30% relative humidity, so started somewhere here. And then you measure the pressure of, it was 70 megapascal, but because you have also some voids, the assumption is that if you insert 1 gram of water, you swell 1 cubic centimeter. But in reality, it's a little bit less because you have some free volume. But the order of magnitude, it's here. And if you, it means that if you are very dry, you have huge pressure. But of course, once you put small amount of water, it is not, you have it drops very quickly. So the work wood is exerting in it to exterior depends on the water content. And if you start from dry and put it in a very humid condition, this is the work 100 gram of wood piece can exert by just swelling. So it's in the order of kilojoules, which is again a huge work that you can do just by swelling. And just so you can break, that's why you can break yourself. So we had some, well, I wanted to have some discussion. So there's elements of controversy from the previous talks. So it is, so my question is it, so the swelling is due to the polymer water interaction, or, and also what is the role of hydrogen bonding in all this? Again, I don't know why it's like this, but so this graph is a heat of evaporation of different alcohol as function of molecular weight. So the one plot here is water. Heat of evaporation of water is enormous. And then it goes linear with molecular weight. And on the bottom is just linear alkane, methane, ethane, and so on. So this is also against proportional to the molecular weight. There is just they just shifted from the linear alkane by about 24 kilojoule per mole. So roughly speaking, in all alcohol, like water or what you have on the cellulose surface, it is this hydrogen bond energy, which is of the order of 24 kilojoule per mole. And this is, if you swell with water, what happens is that water can exchange hydrogen bond with the cellulose surface, but you don't gain anything because you have to break another bond between water molecules. So the net enthalpy between the water of the water swelling should be almost zero. So what is really happening? Why is it exothermal? What was not in the picture of Lost Wolbury is the fact that when you shape the wood, when you shape your gel, for example, regenerate, they are frozen. And what's happening in wood is the same. When cellulose is formed, when the cell wall is formed with matrix, polymer, and cellulose, it's frozen. So they are not free to move. And oops. So I think what is basically happening is the deformation of cellulose or rigid polysaccharides in the matrix component that has to deform during when water evaporates. You cannot leave voids, so they form, and then they store the elastic energy in the structure, and that is giving the spring back when water comes in. So the net heat which is released is due to the fact that it is the spring back of this whatever component, either yes, wrapping up a fibril deformation or small molecules that are coming back. So I will finish with this. We'll have some more discussion.
Very nice talk. I really enjoyed. Can you comment on the role of hemicellulose and the lignin in the swelling of the wood? Because they are a smaller portion, but they, for example, lignin is hydrophobic, right? So, and they have very different structure features inside the wood and compressed wood as well.
So for me, in any case, they are more or less rigid. Hemicellulose is also polysaccharide. It's rigid. And what happens is when cellulose is produced, it is full of water. Okay, and when you dry wood, you are forcing the shrinkage of the cell wall, and just swelling is just a reverse process of releasing its shrinkage. So in general, I might go. So I wanted to say one thing that is known to avoid dimensional instability or to bring dimensional stability is that if you have, for example, hardwood where you have a lot of extractables, or if you can replace water with some non-volatile compounds, that will limit the swelling. And lignin is partly this kind of a little bit flexible filling stuff. Actually, lignification replaces water with lignin. So this is bringing dimensional stability compared to non-lignified component. I think because it's also occupying the space which was occupied by the water.
Thank you.
So what you're saying is that when your building is stresses when you drive, and so in my terms, if you have that, so that means that you should add not a negative withholding pressure, but a positive pressure initially when the stress is released. Is that what?
Yes. So the whole structure in natural state is the swollen state. So what you're doing in drying is forcing it to shrink because and because it's frozen system. So if you have just in your drawing you had a parallel cylinder, and if you have nothing that avoids them to collapse, they should just collapse. But what actually happens is that you have frozen system where you have not perfectly aligned fibers, or you have something in between that prevents them from direct collapsing. So you have to deform to have some contact, to have this van der Waals interaction, whatever, to have this colloidal collapse at the expense of the deformation energy.
So is this at the cell wall level or cell scale?
This is at colloidal level, so molecular to cellulose crystal level.
I mean, you're reducing strains at the scale of, let's say, cellular structure as well by that shrinkage.
Yes, the deformation occurs macroscopically, but the driving phenomena, what is at this colloidal level.
So in reality, the chapter between the cell walls can actually break a cell wall.
I think I haven't observed, but I guess it's between the cell wall. But yes, I didn't bring a microscope. But anyway, wood is weak in if you pull laterally, so it's relatively easy to split, and yeah, you don't really need so much energy to